of the Adage 3000 raster display system to medical imagery. Here's a set of CT slice data, 256 by 256, 40 slices. The 3000 system is being used to fetch a 3D data block and to decode it into parallel slices. Here we're looking at it along the axis of the body. Now we'll look at it front to back, and in a second we'll go through from side to side. The 3000 system is being used here to unpack data which is stored in 8 by 8 by 8 voxel elements, and to bilinearly interpolate the data and display it on the screen. The data is being fetched from a disk file on a VAX 11750 host computer in this case, but I want to emphasize that it's stored on that computer as an 8 by 8 by 8 section, and the unpacking of that into 256 by 256 arrays or 256 by 40 arrays, etc., is all done by the Adage 3000 bit slice processor, resulting in significant speed-ups and a much lower load on the host computer, as well as lower data transfer rates being required. Here you can see the image getting updated at a couple of frames per second. We can extract single slices in any direction and be able to put them together in a Z-buffer type display. This is something we developed for seismic applications, and we're making use of it here to illustrate how it can be used with medical data. You'll note that this is a combination of graphics and image processing capability. The graphics for doing Z-buffers and the mapping to a particular geometric space, and then the image processing type functions for actually warping the data to appear on the image. Here we're taking a vertical cut at an arbitrary angle through this 3D collection of data. Now we'll take a cut at an oblique angle through the 3D section of data. Again, the unpacking of the data and the warping of the image into place on the display screen happens at the speed you see it here because of the use of the Adage 3000's bit slice processor. Here you can see an alternate display format. This time we've taken a lower slice and two side walls. Now we'll take an arbitrary cut, a series of arbitrary cuts actually, through this 3D data set. Here there's a way while we get the next set of data from the VAX host computer. But again, the data unpacking and the image warping are carried out by the Adage 3000 local processor. Just as an example, we'll have a few different color scales in that same set of data. Now let's take a look at what we've done after extracting some contours of one element of that set of slices. Here you can see an outline of it. Now we can fit a bicubic patch surface through that outline. This is an interpolating bicubic spline function. Again, all the transformations, the bicubic spline functions, etc., are carried out locally in the Adage 3000 display system. And of course, we provide high-quality image rendering of this spline surface. So the original data only consisted of what you see here outlined in green. That is, the few grid points happen to be 8 grid points per slice and 12 slices. But the surface is reconstructed using a smoothing algorithm, a spline smoothing algorithm, all calculated locally in the Adage 3000 rotations. Now let's take a look at some work on one of our University of North Carolina, showing some additional uses for a high-performance display system with Programmable Processor.
The program by Greg Abram at UNC runs on an Adage Ikonas computer and frame buffer and uses the binary tree space partitioning algorithm by Fuchs, Kedem, and Naylor. The physician can rotate and slice the picture to see the outside and inside of the artery from any direction. The doctors are particularly interested in looking for constrictions and clots at the point that the artery separates. Since we can slice away the front surface to give a cross-section view of the artery, they can see the interior as well as the exterior. Two 2.5D molecular display, sorting the spheres back to front and drawing each atom as a flat disk painted to look like a sphere. But as the user rotated the molecule, the flat disk popped back and forth unnaturally. During the past year, we've rewritten the program, replacing the painter's algorithm with a pixel depth buffer. Although the new program runs 25% slower, behold. Now the spheres intersect properly and the molecule looks rigid as it rotates. Here you see about 8 updates a second on a 50-atom molecule. The VAX computer reads the hand control and sends viewpoint rotations to the Adage Ikonas, which calculates the hiding and shading and fills in the pixels in the double buffered video frame buffer. When you look into the mirror, you see each dot in the image at its proper depth because the dots are sorted to synchronize with the vibrating mirror. Watch. As we start the mirror vibrating, the single vertical line is drawn out in depth to reveal the letters U and C. Several people can watch at a time without special viewers or glasses. As we move the camera around the mirror for you, your view of the letters changes just as if you were looking at a real object. This gives a strong sensation of depth. Here's a model of a North Carolina landmark, the Old Well. We can supplement the depth perception with joystick control of the object's orientation. We'll hold the camera still now and turn the joystick for you. As it's rotated, the Ikonas processor transforms and resorts thousands of points. Here's what's going on behind the scenes. The CRT is being refreshed from this quarter of the frame buffer display. In the bottom half is the original unsorted object description, lines in 3 space. As you move the joystick, the Ikonas transforms the lines into a list of points, sorts them by depth, and places them into a pair of video refresh buffers. The varifocal mirror programming is by Lee Ching Tsai and Sandra Bloomberg. This device is an inexpensive add-on to a frame buffer that lets you draw lines in 3D.
The appreciating work was partly done by the University of North Carolina, and the original work that you saw using the CT slices was done using the Adage seismic display package, and of the hidden surfaces using the Adage solids display package. Please contact Adage Incorporated for more information.